by Ben. It's going to be focusing on the real-time decision-making applications for the data collection and processing at LHC. And the second part of this talk is more on machine learning aspects. And I presume how to get on top of everything and stay ahead of everything moving down the road. So
hopefully, and what to do if you start behind.
Yeah.
Okay, great. So we had a really excellent introduction to the whole setup from Katerina, so I won't repeat all that, but I'll just very briefly motivate once again while we're doing all this. So at a super high level science at the LHC, the idea is we want to study the structure of the smallest building blocks of matter. So to do that, we build a giant microscope, and you can think of the LHC as a microscope. So here is my length scale of everything. And on the length scales that we can see, of course, human eyes are good enough for doing measurements. But if you want to go down to 10 to the minus 20 meters, that's the magic number for the distance scales that we're probing at the LHC, you need something like the Large Hadron Collider and the experiments at the Large Hadron Collider. And there are many experiments at the LHC, 4 big ones, but I'm going to focus mostly on ATLAS just as an example, but a lot of this applies more generally. Okay. So here is a slide you're going to see several times, which shows basically the pipeline for data analysis collection as well as simulation, and both are going to be relevant for this talk at the LHC. So you've heard this magic 40 megahertz number, 25 nanoseconds before. So this is the rate at which proton-proton collisions are happening at the LHC. And every bunch crossing has about 100 collisions. And those we only usually care about one of those, and the extra ones are called Pileup. And I'll come back to that in a little bit. And the numbers here are in blue for data and in red for simulation. So then you have all the subnuclear and nuclear physics, which spans many orders of magnitude. So like 10 to the minus 20 up to 10 to the minus 15, 1 femtometer. That is super, super fast and is basically not relevant on the time scale of the real data. But then comes the slow part. So the outgoing particles interact with the detector, and the particles are basically all traveling at the speed of light. So the first detector elements are passed after about 0.01 nanoseconds, and then the time that the particles reach the last parts of the detector is about 20 nanoseconds. That's particles traveling at the speed of light all the way through a detector that starts at a few centimeters all the way out to meters. Then you have a much slower effect from the detector response. So you have basically particles traversing the matter, traversing our detector, and they're like ionization signals and other scintillation signals that are slow. And those can take up to 200 nanoseconds. So the numbers to compare with, right, are these numbers compared with the 25 nanosecond number. So we have bunch crossings every 25 nanoseconds, but it takes longer than 25 nanoseconds to propagate the whole signal through our detector.
And how these outgoing particles, there's a mix of momenta.
Oh yeah, so yeah, these particles have a whole mix of momentum, but they're all traveling so close to the speed of light that it basically doesn't matter for the point of view of these numbers. These numbers assume everything going at the speed of light, these ones here.
But you're going to bend them. There's magnetic field, I thought
there's definitely magnetic field, but I mean, the bending is pretty small. So these numbers are like particles with a relatively high energy, typical high energy going through the detector, pretty straight. Okay, so then after we have this detector response, we have to make a decision whether we're going to keep the event or not. So you heard from Katerina, we have this first hardware level trigger, which we call usually level 1. And level 1 has a few microseconds to decide if it keeps the event or throws it away. And then if we keep the event, we have a little bit longer in software, this huge software farm, our detector, to decide if we keep the event or throw it away. And then once we keep the event, we reconstruct the event. So this is now, we read out the whole event and it's off detector, and that takes hundreds of microseconds, which is already pretty slow. And then, okay, at the end we do final data analysis, which people sitting at laptops discussing at meetings, and this takes months. And this may seem not real time, but numbers I want you to keep in your head are for the simulation steps, which I'll come back to later in the talk. The subnuclear physics takes milliseconds. Outgoing particle interaction with the detector takes minutes. And the detector response takes 100 milliseconds. This is really dominated by this part here, material interactions. So if you think of it a minute per event, I need billions of events. Pretty soon you start getting on the time scale of months. So even months actually can be real time, and I'll come back to what that means later.
The hardware trigger has 2.5 microseconds, but you're getting 25 nanoseconds. So does that mean the hardware trigger itself is also buffering?
That's right. All the detector elements buffer, and depending on where you are, you have different amounts of events you store in the buffer at a given time.
I see.
That's right. Okay. So what I'm going to do is I want to, in this talk, I want to talk about various levels and how real-time decision-making or adaptations of fast analysis or fast algorithms can play a role. So let me start with the detector response. And there was some discussion earlier about how we change things both in hardware and software. So you've seen a picture like this before. I'm not going to spend a lot of time talking about it, but okay, our collider-based high-energy physics detectors, they're like onions. Well, I should say that I usually start this talk by saying our detectors are like onions, but my wife corrected me and said they're not really like onions, they're more like leeks. Okay, so they're cylindrical. So the protons and protons are coming like this, and there's a series of detectors out as you go further and further from the detector. But the biggest challenge for data rate is the closer you are to the detector. So the biggest challenge is really the innermost layer. So let me spend a couple of minutes talking about the innermost layers and the data challenges we have there. So here are just some numbers. The background is a pretty picture of what an event might look like at the LHC, but you have a problem not only with the occupancy, so this is like how many particles hit our detector as a function of time. So 0.1% of our pixels in our innermost layer, we have a pixelated detector, are hit every time we have a bunch crossing. That's pretty high rate. And then in terms of like the data rate, it's sort of like streaming live audio from each pixel. Okay, it's pretty shitty audio, but okay. Still, it's a high rate. But the real challenge also is not just high rate, high occupancy, but also we have the thing in a high radiation environment. So this is why a lot of what we do has to be customized. We have to build custom ASICs and custom hardware because it not only has to be super fast, it also has to be radiation hard. And here are just a table of numbers to give you a sense. I don't even look at any of the numbers except the ones I've highlighted in blue. So once again, these are the hit rate, the readout rate, and the radiation damage. And the three different columns correspond to, so run 1, that was up until 2015. This is this is right now, run 2 and run 3. And this is what we're preparing for in 10 years from now. So we're going to increase the rate by a factor of 10, going from here right now to here at runs 4 and 5.
What does radiation damage do?
Very good. So radiation causes a lot of problems for our sensor elements. So it actually can degrade the sensors, and in electronics, you can cause all sorts of problems. You can degrade the components as well as cause single event upsets, problems that basically flip bits from 0 to 1 and make the readout basically not work. Yeah. So the radiation can basically degrade our detector as a time. And the radiation is good, right? Because the radiation is what we're measuring, but it also can hurt our detector.
No, but it's degradation in many forms. One is flipping bits. One is no information.
That's right. Yeah. So flipping bits makes your detector noisy or quiet, and it also can damage the components. More systemic, long-term damage. Yeah. But basically the idea is, so as I was saying, we need to build a lot of custom components because this is like having a super fast camera that also happens to be next to a nuclear reactor. And unfortunately, we don't have any of these from industry, so we have to do it ourselves. Okay, but we have good news, which is that on this innermost detector element, both Atlas and CMS have joined forces, which is kind of amazing, to design a custom ASIC that will be used for the innermost detector readout. And actually, a significant component of this design is happening right here at Berkeley, and one of the spokespeople for this collaboration is actually up on the hill, Maurice. And I just showed a picture of this is a current picture of our prototype chip, just to see that it exists, and we're currently doing some testing with it. But I wanted to connect the design of this ASIC with real-time decision making. So in designing this hardware, we have to think how best we can both read out and utilize the readout structure to have the best offline performance. So for instance, one thing we have to think about is that we don't read out single pixels, we read out regions. And one of the reasons we read out regions is because you want to help recover hits that low energy hits that are next to big hits, because big hits are easier to find. And so you want to ask the question, like, what's an optimal region to read out? So we can do a simple algorithm, like I might read out like a 2x2 pixel region or a 4x1 pixel region. And it depends where you are on your detector. So you can think of our pixel detector like this. It's a bunch of pixelated elements. Our proton collisions happen here, and we have some outgoing particles. And this eta that's here is basically the angle that you make with respect to the vertical. So eta equals 0 is like straight up, and eta equals infinite, or eta equals large is along the beamline. And as you go further out, basically you're traversing more pixels in a row, and therefore the probability to have a neighboring pixel fire is higher if you're at a higher angle. And you can use this information to actually have a more optimal readout region. So in fact, you want the occupancy to be as high as possible in your readout region. Otherwise, you're just wasting readout bandwidth. And so 2x2 is not as good as 4x1. 4x1, the 4 is in the long direction, the direction where you have more pixels that are hit. So these are kind of simple things we can think about. This is just to set the scene for the kind of choices we can make while optimizing the readout. Another very important topic is not just what we read out, but how we read it out. So in the innermost layer, for instance, in all the layers we read out, there's some analog signal and we convert it into a digital signal. And the innermost region, in these pixel detectors, we use an ADC which is called time over threshold. It's super simple. You have some analog signal, and you have some charge deposited, and it takes some time to discharge in our capacitors. And we basically just count how long are you over threshold. And by long, I mean we count like these vertical dashed lines are 25 nanosecond bunch crossings. So everything is tied to this 40 megahertz clock that the LHC provides everyone. And you can just simply ask, how many bunch crossings was I over threshold? And that is proportional to the charge that was deposited. So it's a very simple, I took the TOT method. But there's a lot of choices we can make here. For instance, how many bits do I record? I can actually sculpt, I can have some sculpting, so I don't have to make it linear, charge to TOT. I have lots of choices here. And I just want to say that this charge information is actually critically useful. So offline, this TOT, this charge information, is used for many purposes. For instance, if you had charge information, you can do analog interpolation on the position of hits. So you can say I have some hit pixels. If I have more than just binary readout, I can figure out where the particles were. And that shows the resolution basically improves when you use charge information. We also use charge information for particle identification because different particles have different charge signatures. And we can also look inside a pixel cluster and ask whether more than one particle, because more than one particle would leave more charge than if you had only one particle. So right now, the Atlas detector, for instance, uses 4 bits of TOT in a linear charge to TOT conversion scheme. But we could ask the question, maybe this is not optimal. And we don't have to have the same readout as we have record. So you could imagine reading with 5 bits and recording with 4 bits, or other schemes like that. It doesn't have to be linear downsampling. You could do something more complicated. So we've done many, many studies, but I just want to highlight one possibility where you could imagine I want to compute what the position resolution is of my pixel clusters. That's like shown on the vertical axis here, as a function of the number of bits I have. But imagine I have a scheme where I have a 5-bit counter and I have an n-bit storage. So I want to find what's the best way of transferring 5 bits to n bits, n being at least no bigger than 5. And the position resolution here, so the up is worse. And so if I have only 1 bit, so 5 to 1 bit is the same as having 1 bit to begin with. But if I have 5 bits readout and 3 bits storage, I can actually improve quite a bit versus having 3 bits readout, 3 bits storage. So there are many schemes here that actually might allow us to have some faster algorithms in hardware that are then downsampled in the actual what's actually read out. So it's a lossy readout, but it actually might improve things if we cleverly design the electronics. And there are many more considerations like this that we're currently studying in the design of these ASICs, because we're going to have to now iterate a few times before we go into production mode for designing this new detector.
If you have poor resolution on a single event, but in a capturing in this trigger, you've got multiple events. Is there a way to have them all kind of talk to each other so that a bad resolution systematically off here is effectively corrected by another particle in a different direction?
Yeah, so here it's a bit complicated because we're talking about very local information at basically the bunch crossing rate. Yeah. So this is in hardware, and it's not able to, it can know about the neighbors basically, but not things that are far away.
But I'm just asking more like...
For post-processing, yes. So offline you can use all the available information to improve the resolution. But if we throw away information here, so for instance, if I'm going to record with 3 bits, that information is lost forever. I can never recover more. Yeah. But maybe I can do a clever scheme in the hardware where I have a 5-bit counter but a 3-bit writer, which is effectively better than a 3-bit counter. Yeah. Okay, so that's all I wanted to say for now, just to give you a taste for this detector response. And now I'm going to move to another topic, so a little bit slower time scale, which is the hardware-based trigger. You heard a lot about this in Katarina's talk, and one of the main messages was that you even saw a plot like this, which is that the cross sections, the production of things at the LHC are dominated by kind of boring, let's say usually thought of as boring kind of events that have no electrons, no muons, no neutrinos. And why these things are interesting is because we collide protons, and then we might want to look for rare things like electrons, muons, and neutrinos. So the rate is really dominated by no electrons, no muons, no neutrinos. All the interesting stuff down here has electrons, muons, and neutrinos. So not surprisingly, the recorded events are dominated by electrons, muons, and neutrinos. So here you can see this is the software trigger rate. Basically the total bandwidth is the top, and you can see how it's decomposed into various categories. So this is a similar version of the plot that Katerina showed. And the whole bandwidth here is basically dominated by the electrons, muons, and other electromagnetically interacting particles, whereas the like the quarks and gluon production, which are these blue colors here, are a much smaller fraction. So that means that all those events that were uninteresting are heavily pre-scaled. Means you throw away a lot of them randomly. So you have the usual paradigm, which is that if your favorite process is not triggered on, it's not recorded, and you lose it forever. There are some new paradigms. So one possible way around this is to look for your favorite process, produce an association with something else, and then you can trigger on to something else, and then look at the thing you like. Another possibility, that's what I call the associated production mechanism. And another one, which is this trigger level analysis, is to do your analysis faster and to do it in the actual trigger. Yes?
That association that's for a particular collision.
That's right. That's the key point, yeah. So I have proton-proton collision, but let's say one of the protons, as they were colliding, radiated something. So I can trigger on the radiated thing and then look for something else. Yeah. Okay, so I want to talk about maybe a possibility for a new paradigm, because these have problems. So one is that there's a large effective prescale by requiring this extra thing produced. The cross-section for the extra thing is very small, so you pay a large price. And in the trigger level analysis case, you pay a cost, which is that you still have to pass the hardware trigger. You can never beat the hardware trigger, so all your analysis still happens at the software trigger, and usually the harsher penalty is in the hardware trigger. So what can we do? I told you that we don't collide single protons at a time, we collide many protons at a time, so order 100 protons. So imagine you have, this is like a zoom in of the proton-proton collision axis is like this one. And we're zooming in really small here. And you can see we can actually reconstruct individual proton-proton collisions. This is one bunch crossing, and we have many proton collisions. So let's say, for instance, you trigger on the pink one from electrons. All the other 100 minus 1 collisions are unbiased. They're zero bias, and they, in principle, can have interesting physics in them. So the idea is, what if you triggered on the pink and used all the other colors to look for interesting physics? So we call this a zero bias trigger. And you can ask the question, what is the effective prescale from the zero bias trigger? So the amount of data I have from this, looking at the other collision idea, is the regular triggered data that you have multiplied by the trigger rate divided by the total proton-proton bunch crossing. So with 40 megahertz is what the collision rate happens. And then we can, if we do the analysis offline, it's the HLT offline software rate. And if we do the analysis online, then we pay the hardware level 1 analysis rate. And here are some representative numbers. So depending on the number of collisions you have, this is what we have roughly right now. The numbers that I think you heard also before is that, so 1 kilohertz is basically what we write out to tape right now. And so that means your effective prescale from the zero bias data set would be something like 10 to the 4 if you do the analysis offline, and 400 if you do the analysis in the software trigger. And this is really important because this is like a lower limit. Basically, you don't have to worry. I think there was a question earlier, what if you just didn't record the thing you were looking for? This says that, don't worry, you always have some large fraction of zero bias data that you did record because you triggered on something else. And you can look in these other collisions, which are totally written out to tape. And so this is the upshot. Basically, if you have a zero background search and you can't beat a trigger with an efficiency of 0.02%, you should be using this zero bias data, looking at the Pileup collisions. And if you can do the analysis fast in software, basically that number goes up to 1%. So that's not so bad. And here is just a plot that shows a comparison between the effective prescale as a function of the object energy. This is the effective prescale. So higher number means you're throwing away more events randomly. 1 means you save everything. The blue is if your associated object is a photon, and the red is if your associated object is a quark or a gluon. And as Katerina said, we have higher prescales for quarks and gluons. The prescale for those are like 400 in these units, GeV, and for photons it's a bit lower. But in both cases, so the black solid line here is if you do this zero bias trigger offline, and then the dashed line is if you do it online. So you actually can get a significant improvement over these standard techniques by using the data that you already took, but not the data you would think you should look at. Okay, so this is the upshot. We have this huge data set that we're currently ignoring. New physics might be hiding in these data, and it's most powerful when combining with a trigger level analysis, actually. So at level 1 in the hardware, you trigger on, say, electrons, and then in software, you look at, say, jets that Katerina mentioned. But this requires designing the algorithms now, because they have to be, if they're not in the software, then they're lost forever. And I think that the key takeaway message is that the bottom line for any analysis at the LHC is not 0. So if you don't trigger on it, you're not totally hosed. You still have a bottom line which is much bigger than 0. So that's good news. And I think the creativity, I think the key point here is that the sky and not the trigger is really the limit when it comes to doing analysis limited by trigger. Okay, so now I want to move on and go a little bit further down on this timescale ladder to focusing now on improvements that one could use with a software-based trigger decision and also event reconstruction. So here, the machine learning will start coming in. And once again, I'm going to talk about Pileup. So this Pileup is really a key issue at the LHC because the Pileup is a source of noise. So sometimes the Pileup has interesting events, but most of the time, the Pileup is just soft energy that's scattered everywhere randomly on our event. And that distorts and degrades the trigger performance as well as all of our offline reconstruction algorithms. So this is very similar to an image denoising problem, where I have noise that is randomly put on top of my image. If I think of my detector as an image, a very multi-stack layer image that has a high granularity, we can use machine learning for image denoising. However, our images are kind of interesting looking images. So here's kind of a pretty plot that shows if I have my protons collide, I have my particles go out, this is the surface of my detector, and I measure some energy deposits, say. But this Pileup is kind of interesting because, as you saw from earlier slides, I can reconstruct the vertices of all the collisions. So if particles from Pileup are charged, and I can reconstruct their trajectories, I know if they're Pileup or not, because I can point them back to a vertex. So it's a kind of noise, this Pileup is a kind of noise where I know part of it exactly. I know the charged part of the noise, but I know nothing about the neutral part of the noise. So that suggests an algorithm where I have 3 images that I want to use for denoising. I have the image from the collision I care about, but there's the charged one, because I can pick out the charged part. That's what I call the leading vertex charged. I have the charge from the noise, which I can also identify very well. That's the Pileup charged. And then I have the neutral total for the sum of the one I care about and all the noise. And the idea is to use these 3 images to predict an image which is the collision I care about, the neutral part of the collision I care about, which basically completes the picture. And once I have that one, I can also compute the noise image if I really cared about it. So what you can do is very simply think of this as an RGB image and then do regression, image-based regression. So I take my RGB image, I apply some convolutional neural networks or other modern machine learning techniques, and I output another image. And that's like schematically shown here. So my input RGB image, do some machine learning, and the output is another image, event by event. Yes?
Why would you necessarily need to use convolutional neural nets to do 3-channel image denoising? I mean, 3-channel image denoising has been done for decades without necessarily having to resort to this.
Yeah, definitely.
Why is this better than decades worth of technology?
Definitely. So there's a couple of points. So one is that our images are very big. So convolutional networks are useful because, of course, I can have small convolutional filter sizes for enormous images that are, say, thousands by thousands. So their convolutions there are very powerful. But in terms of like modern machine learning techniques, there are a lot of tricks in training these networks that are very good at identifying the soft, subtle features of our images that are just much better than older techniques. And I'll show the performance in just a second. Yeah. Okay. So here's like a plot that shows this performance metric of how well this machine learning does. And here I want to show, so this is one possible metric, which is we have some objects that we can reconstruct from an image, and they have some mass. And the mass is a really important physical quantity that we want to be able to reconstruct well. So this is the mass after applying some correction for Pileup divided by the true reconstructed mass. So this is what we do. This is in simulation, so I can know the right answer. And ideally, this distribution would be a delta function at 1. And as a comparison between the blue, yellow, and black are different algorithms. And these blue and yellow are sort of state-of-the-art physics-based algorithms. And I want to apologize for my colleagues who came up with their names. I don't know why. One is called Soft Killer, one is called Puppy. So to follow suit, we called our algorithm Pummel, Pileup with machine learning. And the point is that the black distribution is more centered at 1 and more peaked. So that's a good sign. It suggests it's doing something intelligent with respect to the other techniques, which are basically engineered by hand. And the idea here is that you have a fully automated way of optimizing the pileup mitigation. But we can go a little bit further, and just to give you kind of another sense of how well this does, this plot shows the correlation between the corrected mass and the true mass in simulation as a function of the number of extra proton-proton collisions in my event. So the more extra collisions, the more noise. So basically, more noises to the right, less noises to the left. And ideally, it would be correlation coefficient of 1. So we'd be able to exactly get the true value. And you can see the state of the art, the blue and the yellow, they degrade a bit, they decrease. So they're getting worse the more noise you have, which is expected. And also the machine learning one also gets worse the more noise you have. But the key point is that the black and the gray are higher than the other ones and also flatter. And another very interesting feature is the difference between black and gray is where they're trained. So the gray is trained with 140 extra collisions, but tested everywhere. Whereas the black is trained with 20 and tested everywhere. And you can see that, as expected, the ones that are trained at a particular place do better than the one that was not trained there. But they're still relatively flat and pretty close. So that suggests that the algorithm is learning something universal about this pileup that has nothing to do with, not particular about that energy scale that they were trained at, but that can be applied more generally.
Right, actually, a really good argument against the decades worth of image denoising is that those algorithms are designed to make pictures look good, not necessarily to maintain any quantitative correct values about the pixels.
Absolutely, and there's something which I haven't shown you, which is what the images look like. So our images look nothing like natural images. Our images have almost no features, they're very sparse, and they're highly noisy looking. Just even the signal looks very noisy.
Yeah, I mean, right.
So there's no edges, for instance, so it makes it very difficult,
right.
yes.
So, traditional algorithms are designed for natural images and
Yes.
to make them look good. So they're not designed to preserve any quantitative values at all.
Yes, and this will come up also in the next topic, which is that in the science domain we have like clear quantitative things we want to be good. So here, like the mass correlation is a number I can quantify and try to optimize. Although I care about lots of things, not just the mass, but indeed.
It's such an improvement over standard image processing.
So if you're training it to optimize the mass, then how well does it preserve the other things that you care about?
That's a good question. So we haven't done that yet. But in principle, so I just showed the mass, but we've looked at like a dozen or so observables that we care about in principle. And the metric is a standard loss function on the image, so it doesn't actually know about mass. But we could in principle impose that it also preserves the mass, and presumably would do a bit better. But I don't have the plot to show you.
How many other things would you care about?
There's like a dozen or so. Yeah.
Are you also regularizing with any physics at all, or are you just doing pure covenants? You're not saying that you can't have an infinite amount of energy, or
well, so there's the only physical input. Well, there's a lot of physical input now. We're training samples of many years of physics, but the only physical input is the loss itself. We know something about the pileup is generally low energy. So we have structured the loss function such that it penalizes. We want to preserve high energy stuff more than low energy stuff. But other than that, there's basically no physical regulation. Yeah. Okay, so by improving this pileup, we can improve the object performance, both at the trigger level, the software trigger level, and offline. And one nice feature about these algorithms is that covenants, for instance, are relatively simple to apply in a fast way, and also can be applied, for instance, in a nice grid form, in your images in a nice grid form, which is what our trigger level objects look like. So this, I think, is a really key application to apply also in the trigger level. Okay, so the last topic, which I think I'll spend the most time talking about, is about this number, which is the biggest number on this slide, which is the interaction of the outgoing particles with our detector that takes minutes to simulate. So it took a long time, say up to 20 nanoseconds, to happen physically, but the simulation can be extremely slow. And I'll make the connection. So this is not necessarily for real-time decision making, but as I'll come to later, we need real-time speed in order to do this effectively. I think that's what I say here. So yeah, so it's not real-time decisions, but if we don't have fast algorithms, then this is just not going to work, because this number might seem small. I don't care about a minute, but a minute times a billion is a lot of minutes. So then we start to compete with this time scale here, and this actually can be a limiting factor in analyses. So let me first review for you a little bit how simulation works at the LHC. So this is a schematic of what an event might look like. It's definitely not to scale. So you have like 10 to the minus 20 meters is over here, and then there's like a detector over here, which is like meters away. And the only way we can span 10 to the minus 20 up to 1 meter is by carefully considering all the physical components. And just to say, like as I said, this can take a minute per event for the whole thing. But the real key is that it's possible because of factorization. So yeah, technically maybe it's like the Markov property, which is that we can simulate all the different length scales in sequence. So once you simulate one length scale, and once you simulate the n plus 1th length scale, you don't care about the n minus 1th length scale. It only depends on what came before it. So basically what we do is we have a stack of simulators. And the slowest simulator is one I want to spend the most time talking about. But there's many simulators, and most of them are very fast. So let me start by saying the first level simulator is what we call the hard scatter. So basically, you start at the very beginning. You give the simulator the equations of motion, which look something like this. And there are many tools that exist for basically doing phase space integrals against these equations of motion. And they produce, say, outgoing quarks and gluons, which are the smallest length scales probed in a simulation. So 10 to the minus 20 meters. Then you take the output of that simulation, and you feed it to another simulation, which takes those hard, high-energy quarks and gluons and turns those into protons and other particles like protons, things we can actually measure. And this simulation is also not a limiting factor. It's relatively fast. There are many very nice and efficient algorithms for doing that. But then what happens next is those particles hit our detector. So you have these charged particle tracks, and you have depositions in, say, our calorimeter, which what these big blobs are supposed to represent. And the state of the art for material interactions is this package called GANT4. GANT4, I think, is used by many fields for particle interactions, especially in particle nuclear physics. And it includes a series of libraries for detailed descriptions of nuclear interactions and electromagnetic interactions of particles with matter. And basically, there's a series of levels of precision. You can have more precision that take longer. And we have some compromise at the LHC where we say we need this level of precision. It takes however much time it takes. But the key takeaway message is that this simulation basically accounts for an order 1 fraction of all simulation, or all, not just simulation, all computing, computing resources at the LHC. And in general, in HEP, I think it's also a order 1 fraction. Now, after the particle interactions with the detector, there's another step, which is what I mentioned before, that you actually have to then digitize all the signals. And so after this GÉANT simulation says this much energy was deposited in this particular detector element, then we have custom code to do digitization to turn that into the analog signal into a digital signal. And this is sort of custom code by the various experiments. It's very fast, and so usually it's not much of a concern. You've seen this plot earlier. But I just want to mention it here because there's an important point, which is that calorimeter energy deposits factorize in the sense that if I have 4 particles depositing energy in a calorimeter, the energy that is deposited is the sum of the energies from each particle. But the digitization, this detector electronics and all that kind of modeling is not linear. So noise, for instance, nonlinear thresholds, these impose some effects which cannot be modeled by factorizing the deposition of energy from all the particles. Yes?
So what's the model of the detector, or the different components of the detector? I mean,
so it's a very complicated
iron nuclei, sort of on average, or
no, wait,
well, I'm just.
Well, so you say we have a very detailed geometry model of a detector that says there's silicon right here, then above the silicon there's a little strip of aluminum because we have electronics, and then we have many of those segmented. And when a particle goes through, this GÉANT detector literally radiates low energy ionization energy or scintillation energy, depending on what it's going through, off of the initial particle.
So you're modeling a particle, debris, electron cloud interaction.
Yeah, exactly. So the particle, this simulator might say the particle deposited, say 10 keV of energy at this point in space.
Okay.
And then we turn that into electron hole pairs, and then we propagate the electron hole pairs through the silicon, and we record it.
Okay. And that's the level of modeling the
exactly, yeah.
Material.
So it's very detailed modeling of all the low level.
But it's very empirical
Some parts of it are empirical, some parts are physical. Well, it's all physically motivated, but a lot of it's empirical, yeah. But it's supposed to work. It works for all elements, so it's really amazing. This software package is used also for like medical imaging, where you can also shoot particles like protons into skin and things like that. But
it's a different kind of modeling from the collision model, the original collision modeling.
yes, so this GEANT model is totally different than the other simulators I talked about earlier. Yeah.
It's more of a material science type of thing.
Yeah, that's right. Yeah, as opposed to like high energy, like detailed high energy physics. Yeah. Okay. Great. So my goal for the remainder of this talk is basically to talk about how we can replace or augment simulation steps with faster, powerful generators based on state-of-the-art machine learning techniques. And basically, there are many steps we could try to speed up. I just told you about all of them. But the lowest hanging fruit is to attack the slowest part, which is the interaction of particles in a calorimeter. And why is the calorimeter the slowest? Because what's the point of a calorimeter? The calorimeter is to stop the particles. So basically, you have like an electron hits a calorimeter, and I try to stop it. So to stop it, it has to radiate a lot of particles. There's very detailed interactions of those particles inside the detector volume. Whereas for a tracking detector, like a piece of silicon, if I shoot an electron through the silicon, it has low ionization, and so there's only a little bit of energy deposited there, and it's relatively fast to simulate. So maybe I just very quickly say like why you should care. So many analyses at the moment are basically you're forced to use this GEANT-based simulator because we have fast simulators, just not good enough. And I just for comparison, I show you this is the same plot I showed earlier, but this is 3 billion events. This is the cross-section of particle collisions, and this is 3 billion events at the upgraded LHC, the one that we're going to have in 10 years. So everything below here is more rare than 1 in a billion. So if you want to have a background, the same number of background events simulated as you do in your detector, you're going to have to simulate more than 3 billion events. Now, we're more clever than just generating 3 billion proton-proton collisions, but this just sets the scale for how many kind of events you need. I mean, even at this point, right, W bosons are in the billions of events, and we're going to record most of the W boson events, so we need to simulate also a lot of W boson events. Okay, yeah, so this is just my warning. If we don't do something, basically won't be able to do data analysis at the upgraded LHC, and if we do something now, we can save a lot of money, which makes people happy. Okay, so how can machine learning help? So training neural networks is very slow. I think people here who have trained neural networks, they can take days to weeks to train a good neural network, especially a complicated one. Physics-based simulators are also very slow, but evaluation time of a neural network is extremely fast. So if I can train a neural network to learn my physics-based simulator, I can then have a surrogate simulator that's extremely fast to evaluate. And so basically what I want to do is learn how to generate showers in a calorimeter with a neural network. Okay, so how does this work? There are many possibilities for turning a neural network into a generator, but this is a very particularly powerful one. It's a relatively recent idea called a generative adversarial neural network. And the idea is, what is a generator? A generator is nothing other than a map, a function between noise and stuff you care about. So I make one of those, make it a neural network. So I have a generator neural network, a generator network that maps noise to images. Images being like my calorimeter energy deposits. I have another neural network that classifies this image as being from the generator or from the physics-based model. And they compete against each other. So this one tries to generate realistic-looking images, and my other one tries to tell if they're from the neural network or from the physics-based simulator. And when this one is totally confused, when it can't tell if it's from the physics-based simulator or from the generator, then the generator is really good. And that's the idea, how you train these kind of things. Okay. But it's more complicated because we don't just have single layers. So this is a kind of a schematic view of what one of our calorimeters, the Atlas detector, looks like. So you see a particle might go through here and go through 3 layers. But you might notice that, first of all, these 3 layers don't have the same granularity. So the pixelation is different in all 3 layers. That's a key complication. But there's another complication, which is that the particle energy, the energy spectrum in this calorimeter layer depends on the energy spectrum in this calorimeter energy layer. So it's basically like a short movie. And that makes it also kind of complicated. But we have a model for doing this, and I just very quickly flash up what our neural network design looks like, and I don't want to go through all the pieces here. But basically, you feed in the neural network the energy of the particle and the type of particle. So you say I want a pion that has 10 GeV of energy, and then what we do is we generate one image. I'm not going to talk about this. Lagan is a method for doing locally connected instead of convolutional layers, but it's basically a convolutional neural network. And then to match it to the next layer, we resize that image. So we take our output of our first generated image, resize it, and then we have another randomly sampled image, and we combine the two. So we combine the first image with the second one. This gives us some causality between images. And then we do the same thing for the third layer. So we have another layer which is combined with the output of the second layer to give us the third layer. And that generates 3 images. And those 3 images are supposed to correspond to 1 calorimeter shower. And I can, of course, ask the network to give me many, many showers. I'm not going to show you the architecture for the discriminator, but the idea is kind of similar, just in reverse. OK, so this is what it looks like to generate many, many showers. So the top row here are the average images for a 10 GeV electron for the physics-based simulator in the first, second, and third layers of this liquid argon calorimeter. And these are the images, the average images from our neural network. And this, remember, this is called a generative adversarial network, so it's called a GAN. And this is for a calorimeter, so we call it CalOGAN. We can look in more detail not just about averages, because of course the averages are important, but we also need to get the fine details of the distributions correct. And there are many, many more plots one can look at. But it turns out it's actually, of course, very hard to visualize the space in, say, 1,000 dimensions. If you have a 30 by 30 image, then very quickly becomes very large. But we can take slices in dimensions that we know are rather important. So for instance, this is the energy deposit in the first layer. And here there are many lines that correspond to the physics-based simulator. Those are the filled histograms for electrons, photons, and charged pions. And then the same for our generator, our neural network-based generator. And you can see there's a qualitative agreement between the various shapes, which is very good. But of course, there's also some room for improvement. So you see some features that are present in, say, the neural network that are not present in the physics-based simulator. So there's clearly room for improving upon what's shown here. But I really like this plot because, of course, the generator doesn't know about, the neural network doesn't know about the shower shape. It knows about the full 1,000-dimensional space. And it qualitatively reproduces this image. In fact, one could actually input this image into the neural network to impose that it learns this one well, as was discussed earlier with the mass. But for now, it's used as a holdout to do validation. But in principle, I could force it to learn this well in the training of the neural network. But this is really the punchline. And the punchline, as I said, I started by motivating this all about speed. So it has to perform well, but it also has to perform well fast. So here's the physics-based simulator. And this is how long it takes to generate 1 calorimeter shower for some hardware on CPU. And if I use the same CPU to generate my 1 shower in the CalOGAN, that's from this number to this number, you see it's much, much faster. So that's good news. That's how I started by motivating this whole thing to begin with. And you can actually gain by batching. So instead of generating 1 shower at a time, you can generate many showers. And you actually don't lose that much. You actually gain a bit in speed. And a typical event at the LHC might have 1,000 particles going out. So you might need to generate 1,000 showers at a time. So this is a relevant, realistic number. And of course, you can also gain from GPU. So if you go to GPU, and this is the number for 1,000, you see really there's a lot to gain here. So maybe 5 orders of magnitude. And this isn't quite fair because, of course, CPU, so Geant on CPU, this number will continue to get better. And CPUs for neural networks will continue to get better. But this just gives you a rough idea. There are significant gains in time that seem possible with techniques like these generative adversarial networks.
Is there any effort to port Geant 4 to GPU?
There is an effort. And there's also an effort to take techniques like the generative adversarial networks and port them into Geant. So there's this Geant 5 project, which is the successor of Geant 4. And there's many ongoing projects, both on the regular standard Geant part to speed it up, as well as integrating machine learning into various components. OK, so that brings me to the end. The LHC is really a unique science tool with extreme challenges. And a lot of those challenges are related to the data rate. And we need both real-time decision-making solutions, but also real-time algorithms for offline that empower the science to happen. I think there are many exciting opportunities for new ideas to fully exploit our data. And we have to do this because we need to make sure that no stone goes unturned. We'll not have another LHC. And so we need to make sure that we really fully exploit the data analysis that we have at our hands. That's it.
Jake, any further questions?
One comment about the GANs that we're concerned about. We love these devices, but they have this problem that, in principle, the generator can generate data in a subspace of the true data space, as long as it's doing a good job. And one of the problems is when your space is thousands or millions of dimensions, there could be some kind of fractal subspace. So in any projection, it looks good, but in fact, you're only seeing some part of the data subspace. And I think that's an open question that almost all scientific uses of GANs are going to have to address.
Absolutely. So we've done some tests to try to probe, for instance, if it's memorizing or if it's only looking at a subset. It doesn't have the same entropy as the original data set. So you can do some tests, for instance, by looking at the nearest neighbors within sample and outside of sample. That's what these plots are supposed to show. Basically, I look at the nearest neighbor, the nearest GANT image, or the nearest GAN image, and they're about the same distribution. So that's a good sign to suggest that it's not memorizing, nor is it, and also has the same entropy as the original data. But this is a key challenge, as you said. For us, we have an interesting task because we have really good fast simulators already. And those fast simulators, we know exactly what like manifold they live on because they're just Gaussian. They're like multidimensional Gaussians. And so the first thing to do is to try to beat them, to see if we are at least doing as well as those things. And then we can try to go extend beyond that and try to match higher dimensional features that those generators by construction can't handle.
One other comment or whatever question is you're putting in the GAN at the very high level, like very late in GEON. So you're saying getting GEON to do the whole thing, and then you're asking, can I reproduce the whole thing?
That's right.
Probably if you look under the hood of GEON, there's particular submodules in GEON that are taking all the CPU. You could run your machine learning there and replace modules of GEON. And that, like in the climate world, I think that's what people are more thinking in terms of.
Yeah, so in fact we've thought about, we made some choice here about what step to do it. So it's an end-to-end in terms of GEON. And you could, in principle, for instance, have some kind of network that learns like a recurrent kind of thing that learns like all the energy depositions as like the shower propagates. So then you only have to learn like the part that the kernel basically
It might be smaller, yeah.
Yeah, that becomes kind of complicated very quickly because there's lots of physics models in GEON that depend. You become like you can become detector agnostic, which is good. So this is not detector agnostic. It depends a lot on the structure of our calorimeter. But if you learn the actual probability distributions inside GEON, then you can be detector agnostic, which is very powerful. And I think something like that will be where the full gains are going to be realized. But for a particular experiment, if I know I have the Atlas experiment, then I can try to gain by training exactly on that. Yeah.
So I think you were hinting at this in terms of modifying your loss function so that you get the correct distribution of types of events. But isn't the generator or the discriminator now just basically looking at individual events and trying to say, are you real or are you not, rather than looking over the entire distribution?
Okay. Oops.
I may have stated that wrong.
Yeah. So it's true the discriminator acts on individual events, yeah, but the loss is at a batch level. And so what we have, so this is the discriminator network now. And so you have your input images, and we have some convolutional, locally connected, but they're like convolutional layers to process them. But then we have mini batch discrimination because exactly the point that if you just look at individual images in the loss, then you won't reproduce the data entropy because you only can see individual examples. But here you look at an ensemble, a batch of examples all at once, and you have some features which are at the batch level that also go into the loss.
Other questions?
And so the GAN distribution you're going to get, you can get close, but it won't exactly correspond to the true distribution.
Yeah.
So for what sort of application is that enough?
It's a good question. So the real question now is this better than the current fast simulators? This is like a system. So the way the current fast simulators work is that, like I was mentioning earlier, there's basically a bunch of Gaussians that are sampled in a space, like in these spaces, for instance, that we know are important. And they miss higher dimensional correlations in the data. And we can, first of all, compare with those. And these techniques are systematically improvable. So the problem with the fast simulators right now is if you want to add a new feature, you have to manually change how things are set up. This will get better if like someone has a new idea for how to improve GAN training. This benefits directly from that. So we have to first beat the fast simulators. And the real problem with fast simulators right now is that the current Atlas and CMS experiments, their fast simulators are proprietary. So it's extremely hard to compare this unless you implement this in the full Atlas, say, software framework, which we're doing. But you have to convince 3,000 people with an aging code base that something new like this should be implemented, and that takes a lot of work. And that's happening, and that's where the key comparison will happen first, is to look at the standard observables that people use to train the current fast simulator, and then to look at higher dimensional features, like in a physics analysis that's particularly sensitive to the shower modeling.
Questions? All right, let's thank Ben again. Back at 1:30.